Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So in this session, Tom and I are going to talk a little bit about what we do in the Empirical Software Engineering Group at Microsoft Research, and then Peter Rombach is going to tell us some about what he's been up to lately. So originally, Nachi Nagapan was going to give the talk. He couldn't make it, but this really is the three people that make our group are myself and Tom and Nachi, and then Brendan Murphy is kind of an associate at Microsoft Research Cambridge, but does a lot of similar stuff. We do a lot of work with him. Those are our pictures over on your right. So in our group, we have kind of two main goals. One is to gain insight, understanding from product processes, from people, from customers. And we do this generally, well, if you went to the keynote this morning, Wolfram talked a little about what we do. We gather quantitative and qualitative data. We do empirical studies to try to understand how things work. And then once we're able to test a hypothesis or understand how a certain process works and what its effects are, we try to help software development teams by providing tools when we can, evidence and database tools, and then also making recommendations, providing best practices and suggestions for them to improve their process. And one of the kind of unique things about working at Microsoft Research, and some of these may apply to some of you, especially if you come from industrial backgrounds, is that because we're Microsoft, and Microsoft is in the process of producing software, we have easy access to industrial data. So if we have some question that we want to answer, we can go to product groups and talk to them and gather their data. And by having access to the data and the people, that allows us some insight that sometimes is more difficult to do in a university setting. And then likewise, if we come up with some tool to help developers or some practice to put into place, we have a number of product groups that are interested in getting that feedback from us, and they can immediately put it to use. So if we come up with a tool, we can immediately tell if that tool is actually useful or not, because people will begin using it. And then, of course, we've got a number of people in other areas like machine learning, computer vision, and other things that we can collaborate with within Microsoft Research. And then we have the opportunity to collaborate with people outside of Microsoft Research as well. And some of the people that we've collaborated are even in this room. To give you an idea of some of the people that we've collaborated with, here's a map with the locations of people that we've collaborated with. The black push pins are our labs, and then orange are locations of collaborators, and then the list over there on the side. So like Harold came and visited us for twice for a couple months in the summer. We're always looking for good interns to work with. We're definitely open to collaboration with both university and industrial types. So to give you a feel for what we do, I wanted to present some of kind of a smattering of some of our results and tools that we've come up with in three main areas. This is what we've been looking up over the past few years. I'm going to talk about socio-technical congruence, which is kind of the interplay between the software itself, the entities that we produce, and the developers, and how the human side of software engineering comes into play with the technical side. And then Tom's going to talk about some work looking at bug reporting and triage, and also analytics and data-driven software engineering. So both my PhD dissertation and what I've been doing at Microsoft is really focused on the people. And Bjarne Strostrup is considered the father of the C++ programming language. And he said, design and programming are human activities. Forget that, and all is lost. And so in our quest to kind of understand software development in the large, we've been looking at people, and that's led to some interesting insights. So I'm going to present three studies. The first study is where we decided to look at distributed development and what, if any, effects it has on quality. And for each of the slides, we have a list of who took part in the study. So this is myself and Nachi, and then my advisor at the time, Prem Devambu, and then Harold Gall, who's right here, and then Brendan Murphy from Cambridge Research. So the question really is, in this global economy, you've got a lot of international companies, and sometimes for economic reasons or talent location reasons, there may be some reason to develop software in a distributed way, have different parts of your system developed on different continents. And there's a lot of challenges that people are aware of. There's a lot of research in this area. But up until the time that we studied this, and since we published our paper, there have been other similar studies later, we kind of know what is the effect on code quality of having a very distributed, internationally distributed software development project. And so at the time, this was about a year after Windows Vista came out, we thought, well, this is a perfect case study. Windows Vista was developed on a number of continents, people around the world. If you want to understand the effect of distributed development, let's look at what happened with Vista, and that maybe can give us some insights. So what we did was we divided Vista up into its constituent components. So think of individual binaries within Vista. You have shared libraries, you have applications like Notepad and Explorer. And for each of these components, we identified where the developers were that made contributions to these components. So this is an actual component, cmroute.dll. And I've anonymized the names, but this actually is the breakdown of the locations of developers. The numbers next to each developer is how many contributions, how many source code commits they made to the code that went into cmroute.dll. We did this by mining data from the source code repositories, looking at changes to source files, and then what source files were compiled into an individual DLL. And the reason that we use this DLL, or the binary level, is that when Microsoft gets bug reports, we can tie them fairly accurately down to the binary. It's not always easy to identify one individual change or one individual source code file that was the cause of the bug. So we did this for all of the binaries in Vista, and there were thousands of them. And I don't know if you can see the percentage. What we did was we categorized them into a number of different levels based on how distributed the developers were. So if the majority of the developers that worked on a particular binary all worked in the same building, then we'd categorize the binary, the building level. Cafeteria, one cafeteria at Microsoft can serve a number of buildings, but usually those buildings are in close proximity. So you can see 2.3% of the binaries had, most of the developers were not in the same building, but were in a tight group of buildings. And then campus, locality, which is like kind of a city, suburban region, all the way to continent, and then at the world level. A world level means that we couldn't identify any individual continent that the majority of the developers worked in. So you'd have some perhaps in Asia and others in North America and others in Europe. So this is the breakdown. And although the majority are developed at the building level, when you have about 3,000 to 4,000 binaries, even 6% at the world level, that's still a fair amount of distribution. So we have a number, enough samples at each level of distribution that if there's an effect, we'd expect to see something. And our hypothesis, at least, based on the prior literature, is that as the level of distribution increases, they'll have a negative impact on quality. We measure quality as the number of bug fixes that need to be made to individual binaries. And the way that we did this was we used standard method linear regression, standard method in statistics. And this is basically what our data looked like. For every binary, we had a binary variable, I shouldn't say binary, a Boolean variable that indicated the level of distribution. And we did this because we didn't expect that there's actually a linear relationship between distance between buildings and cafeterias and campuses. We wanted to determine if there's a particular level where above that level, the quality really diminishes greatly. And in prior research, a lot of people have found that the number of developers working on a particular piece of software is strongly related to post-release quality. And we wanted to control for that. And that's why I included the number of developers in our models. And this is the results of our regression model. So if you haven't had to interpret linear regression models in the past, I'll kind of break it down for you. Each variable is quantifies, or each row represents the binaries that were at that level of distribution. And the percent increase is the percent increase in number of failures relative to binaries that were developed by developers in the same building. So what this means is binaries developed by developers in different campuses had on average about 6% more post-release failures than binaries that were developed by developers in the same building. And then the significance, the p-value on the right, is the odds, gives you the probability that what you're saying is just due to noise in the data or high amounts of variance. So when the p-value is below 0.05, that's kind of the magic cutoff in statistics, that means that it's a statistically significant result. So for different localities, it looks like we have an 8% increase, but the p-value of 0.457 means that there's so much variance in the data that we're not sure whether that's actually a real effect or if it's just a function of not having a large enough sample and so much variance. So there are only actually two, in this case, two levels of distribution where we actually saw an increase. And although it's not trivial, I mean, 4% is nothing to sneeze at, but it's not as high as we expected. We thought we'd be seeing increase in post-release failures of 20, 30, maybe 100% in terms of post-release failures, and we didn't see an increase that high. So this is generally a good result. We're happy to see this, but when we talked to managers and people in Microsoft, they said, well, that's really surprising because we've run into problems with distributed development. And so we kind of did an informal survey of managers in Windows to see, well, how were you able to do this level of distributed development without a negative impact on post-release failures? And this is the list of things that they gave us. I just wanted to focus on two of the points that they felt were perhaps the most important. I want to stress that we haven't shown a cause relationship between any of these points. These are all kind of hypotheses about what went on. All of these things went on during the Windows Vista development cycle, and that managers believe had an effect on, helped in post-release quality. So one was daily synchronous communication. So on a daily basis, teams would either come in early or stay late so that teams on different continents could communicate in a synchronous, usually like a video chat, to say, here's an issue that we need to work on. And that allowed them to catch problems before they escalated out of control by the end of the week, or work the problems that escalated up the management chain and became a real issue. So this allowed them to catch things early and deal with some of the communication breakdowns that are often associated with distributed development. In addition, one of the problems that's been mentioned in literature is if you have teams in different places, they may use different tools or different processes. And so that works fine and well while they're doing their own thing, but when it comes time to integrate all of their changes and release something, you run into major problems, and that's what leads to post-release defects and also delay. And in Microsoft, you have a number of managers that started out in Redmond and then left and went to the individual sites, and they took with them the process, and they took with them the understanding and knowledge of tools. So you have the same people in India, the different people in India, but using the same tools. They're all using the same source code management system. They're all doing bug triage in the same way. And by having this consistency throughout the process, they avoided some of the problems that other projects have shown. So this is kind of, and there is a paper associated with this, and I'd be happy to talk about any of these other points or any more details of our analysis offline. But this is kind of a teaser to take a look. And we're actually interested in replicating this study on some other projects, both within Microsoft and in the open source realm, actually. So that was geographically distributed development. We've also looked at organizationally distributed development. So what's the effect of the structure of your organization and how it develops source code? And this is motivated strongly by Conway's law, which is from the 60s. So Conway said that organizations that design systems are constrained to produce systems which are copies of the communication structures of these organizations. And later, in Brooks' essay, very famous, The Mythical Man Month, he said that the quality of the product is really affected by this structure. So basically, Conway is saying what you develop is going to look like the structure of the people and how they work together. And Brooks says, if you have a bad structure, that's going to lead to a bad product. But up until this point, there hadn't been some empirical evidence. So we decided to look at this question. And so we also did a study of, again, Windows Vista. And what we did is we came up with some organizational metrics. So let's say that this is some product in Microsoft, and it's over in Redmond. So we have Peter Lee at the top. And what we did was for every binary, every component within Windows Vista, we identified where are all the developers in the organization that made changes to that particular binary. And then we said, well, let's look at how cross-cutting those developers are in the organization. So let's say that for one particular binary, you have developers in this organization or this team and that team. And so one of our metrics was how high up in the management chain do you have to go before you can find a common manager over all of the developers that contributed to a binary. We also looked at how many different organizations. So let's say Peter Lee is over here in Redmond, and Andrew Blake, who's the head of Microsoft Research in Cambridge. There's some developers under him that also make changes to a binary. So we counted how many different organizations made changes to a binary. So this is just a few of the metrics that we looked at. The number of engineers that made edits to a particular binary, the number of engineers who worked on a binary and then left the organization. Often people have some domain knowledge that's only in their head, and when they leave, they take domain expertise with them, and that knowledge goes away and leads to post-release defects. We identified the organization, the level that we could identify 75% of ownership. So if we had to go up 3 levels versus 1 level, lower levels of ownership would lead to fewer post-release failures, the number of edits made by the owning organization, a number of measures that tried to capture how distributed across the organization a particular binary is. And then we built a defect prediction model that basically said what is the relationship between these measures and the quality of the software. And then we compared that to prior studies. So we have a long history in Microsoft of using defect prediction, and I'll talk a little bit next about why we do that. But here are a number of types of measures that we've used. So we've used pre-release bugs. So what's the correlation between bugs before you release to bugs after you release? What's the relationship between test coverage, dependencies in the code? So these are a number of metrics for the code, and then the precision recall, which are just measures of accuracy for a defect predictor. And what we found is that when we look at the organizational structure, which is a measure of the people, not the code itself, the accuracy of a defect prediction, or rather relationship with post-release failures, is higher when we're looking at the people than at any actual measure of the code. So it appears that there's a very strong relationship between the organization that creates an entity and the quality of that entity itself. And again, this is, so far, it's been tested on Windows and a few smaller products. I'd like to replicate this on both in other industrial contexts and also in an open source context to see how universal this is and how specific it is to Microsoft. So I think it's important when understanding empirical results to recognize the context because it may not be universal. But yeah, I guess I should have brought that up. You saw a strong relationship with organizational metrics than traditional measures of software. And then so I just showed you the results of some defect prediction. But we use defect prediction a fair amount in Microsoft. And the reason is that we want to ship really high quality software. But we can't ship perfect software. If you wait till it's perfect, you're never going to get it out. And so you're limited by both time and by money. You can only have so many people working on things. We have to ship at a certain date. And so if you only have a certain amount of time and money, well, what do? Well, this is where defect prediction can help. If you can identify the pieces of the software that are most likely to have problems, then you can focus your time and your money on those areas. Those are going to give you the biggest bang for your buck. And so the standard thing that we do is we gather a number of metrics. So churn and dependencies are standard metrics. The organizational metrics I just described are some metrics. There's a number of different types of metrics. We feed that into a machine learning model. So we've used naive Bayes, logistic regression, principal component analysis. And then after we train that model on a subsample, maybe a prior release, it develops, in the case of like logistic regression, a number of coefficients. And then we feed new data into that model. It makes predictions, sometimes in the form of classifications. It'll say this binary will be defect prone and this one will not. And sometimes a ranking from top to bottom. Here's the most defect prone to the least defect prone. And then you can use that to make decisions about how you're going to allocate your resources to improve your quality. And so one of the things that I've been looking a lot at is relationships between people and artifacts in software. So there are a number of types of relationships. One type of relationships is by looking at developers' contributions. So if we can look at who's contributing to components and how components are related, we can build like a social network of developers where the connections between developers are actually how many items they've worked on in common. There's also dependency relationships. So for a particular component, you can see what depends on that component and what other components does that component depend on. And so you have all these types of relationships. And so the question that we ask is, are the relationships and the topology, the networks formed by these relationships, are they reflective of actual failures, post-release failures in the field? And so what we did was we built networks based on these relationships and then used an area that we actually borrowed from sociology called social network analysis. In social network analysis, there are a number of forms of centrality. Some of these you've probably heard of. If you have a network, in this case formed by pieces of software, degree centrality for each node is simply the number of edges incident to that node. Closeness centrality for a particular node and network is a measure of the distance between that node and all other nodes in the network. Betweenness is a measure of how many of the shortest paths between all nodes in the network a particular node lies on. Eigenvector centrality is computing actually the eigenvector of the adjacency matrix, and it's similar to what Google uses for their PageRank algorithm. So there are some others as well. These are all measures of the importance of a node in a network, and they're all measures that are on a per node. And in our case, nodes in the network are binaries and people. So to give you an idea of what our networks look like, we have our developer relationships leads to a contribution network. So in this case, circles are binaries, and the rectangles are actually developers, and we can build this huge network and then look at the social network analysis metrics for each of the nodes in the network. And then also we have a dependency network. So dependencies are just based on types defined in one module are used in another module, inheritance relationships, RPC calls, reading registry values that another component writes, method calls. And so that was our dependency network. And then we can combine them into what I call a socio-technical network. So this has both people and their relationships to software and the relationships between individual software components to build a network. And so what we did is we built each of these individual networks and then computed these centrality measures. And, and here are the results. So precision and recall are both measures of the accuracy of a defect prediction model. And what we found was when we combined both the social and the technical relationships, we got precision and recall values of about 0.76 and 0.7, which is high enough that we can begin to use it to make resource allocation decisions. And so initially what we found is the more information you include, the better your results will be. That may not actually always be the case. It can be the case that when you add additional measures, your results actually your accuracy actually goes down. But we also decided to replicate this on Eclipse. We did this when I was in grad school. So at Microsoft, we don't look at a lot of open source, but I went back to school and said, well, let's see how well this works in another context. So for Eclipse, we gathered 6 releases. And in each case, we would train the model on one release and then evaluate it on the next release. And again, our precision and recall was actually fairly high, even better than in the case of Windows. And so this gives us confidence that this network-based prediction, building these networks and then looking at the topological properties of the components in these networks, actually may be more general. So far, we've tested it on Windows and Eclipse. But for universality, we hope to be able to test more things. So that's kind of a smattering of some of the things that we've been doing in the area of socio-technical congruence, looking at the developer behavior and what that can tell us about software quality. I'm going to turn it over to Tom now to tell us about bug reporting, triage, and data-driven software engineering. Yeah, actually, I'm 5 minutes ahead of time, which I'm sure you're all sad about. So sure, throw a few questions at me.
Could you please tell about some insight about the distribution of the bugs amongst different files? Do they themselves follow like a 20-80 kind of rule that 20% of the files have 80% of the bugs?
Okay, so that's a really good question. So normally, for pre-release bugs, that is the case. We see a really skewed distribution. For post-release bugs, that actually is not the case. Believe it or not, and this is really kind of surprising because most distributions don't look like this in software engineering, but it follows a fairly normal distribution where you actually have like half of the binaries actually have half of the bugs, which is surprising. But there is a big difference between the pre-release and the post-release bugs. So yeah.
So when you looked at these, so you trained your model on the previous set of, you trained your model on the previous release and used it for the next release for prediction. So there also, did you see common things like the files which were likely to have bugs in the previous releases?
Yeah, so that's definitely the case. If a component is problematic in one release, it is almost always going to be problematic in the next release. Yeah, I mean, there are cases where, so the difference is where sometimes there are no changes to a component. So if in release 1, there's a lot of churn, and then in release 2, no one changes anything, then we don't see as many post-release failures. And also, there's new components that are added to the system. So obviously, in that case, while we're building coefficients and building our linear model based on data from a prior release, we don't know anything about that particular component from the prior release because it simply didn't exist. And yet, what the model has learned actually is fairly accurate on the data for the new components that came into existence in the second release.
And do the bugs revolve around that particular files, like those files which make use of this particular file? Are they likely to have more bugs? Or
So I think there has been some, is that what you guys did with, Lori Williams has a paper, I think, with, that I wasn't involved with, but I think it looked at like the relationship between components that had dependency relationships with really buggy components? I believe the answer was, yeah, there is some relationship, but that's off the top of my head from that paper. I'd have to, but if you follow up with me a little later today, I can double check on that. Any other questions from anyone? I've answered every question you might have. Great. But feel free to talk to me offline as well. Oh. And Tom thinks people might want to listen to him.
Thanks. So I'm going to talk a bit about bug reporting and triage. And I first want to put the focus a bit like on bugs. And so at Microsoft, you have like lots of tools, but you also have like many toys. Like you have bug vacuums, you have like many bugs, and you also have like bug charts where we collect our bugs, and you also have like watches where we can observe bugs, like how they behave. And the reason why I'm showing this is like I want to show that bugs are not just a big thing for software developers, they're also a very big thing for kids. And actually, there's one book which I like quite a bit. So it's called Bugs, Bugs, Bugs. And this book has one special thing. It actually comes with a bug tracker where children can track the bugs that they found, that they observed in nature. And I like this bug tracker very much because it's the same style as we use in software development. Like you can see here, it's essentially just a table. We have like different rows to describe a bug. Like for example, kids would like draw a picture of a bug, say if it would fly. And if you think about software development, it's the same, except that we just have different names for the columns. Like we ask for bugs, like what are steps to reproduce? What's the type of the bug? How was the bug found? Who should be assigned to the bug, and how severe was this bug? And there's one difference, though, in software development, and that's the people. Because software development, bug tracking is a highly collaborative process, while the bug tracker that I showed you just for kids, it's usually just for one kid, maybe for parents, but that's it. And so I don't know, like, how many people of you have like experience with bugs? Like, who has submitted a bug report? Okay, who never heard anything about bugs? Okay, so I can go quickly over this. This is just to give you an idea like how bug tracking works. Like essentially, when you have a failure in your software, often what you get is like you get an error message like the application keynote has unexpectedly quit. And what you can do then is like you click on submit bug report. And depending on what kind of system you have, it might send a bug report automatically. But still, many systems ask for like manual bug reports. And that's what you get. For example, if you file a bug report for the Apache web server, you get like this page here where you have to first say which version, how severe the bug is. Then you have to provide a description, a URL. You can assign the bug to people, and so on. So this is like the information that you as a user send to the software developers. This is how it looks then in the bug database. Essentially, all fields are filled in, and then there can be some discussion about the bug, like in a public forum. And also, bugs get assigned to people. So this is what I'm showing here, like this bug would be assigned to Steve. So that's just to set the common ground, like that you know what bug tracking is about. And so one thing which we did is we looked, like you can imagine that at Microsoft, bug reports are quite central, because that's essentially where we get feedback from customers and also where we organize our work. And like one study which we did like almost 2 years ago is with an intern, Philip Go, where we looked essentially which bugs actually get fixed in Windows. And so when I talk to people, many people are surprised that not all bugs get fixed. So some people are really shocked, but actually there are often very, very good reasons not to fix a bug. And so here are a few examples of bugs where you might decide not to fix the bug. For example, if you have a bug which occurs very rarely and affects only few users, like it affects only Tom, and the bug is very, very expensive to fix, like you have to redesign entire Windows, then probably Microsoft won't fix the bug. Or, like, there are actually quite a few empirical studies which show that fixing bugs is much more difficult than implementing new features. So the risk of introducing a bug, so I think it was like, most studies had like numbers like twice as risky as implementing new features. So that's why you also might decide not to fix a bug, because you might have to change a very complicated piece of code and you fear that you might introduce new bugs. Or sometimes it happens that people already started relying on some existing behavior and you cannot change the behavior because otherwise you will break the system. So the research question that we had is we essentially looked at factors related to people and bug report edits, and we wanted to see if there's some influence on whether bugs get successfully resolved as fixed. And there were two main reasons why we were doing this, because first, it helped us to identify inefficiencies in the bug triaging process. So bug triaging is a process about deciding which bugs get fixed and by whom. And it also helps to inform the design of tools and policies for bug triaging. And just to give you one more number why bug handling is actually quite important. So for Windows, we have about 2,000 developers who write Windows code. But if we look into the bug database for Windows at Microsoft, there are more than 24,000 Microsoft employees who in some role participated in one bug report. So for example, if they submitted a bug report or provided feedback on a bug report, they were assigned to a bug report, or they tested a bug report. So you can actually see that the number is much higher. And if you think about Windows, so that's just the Microsoft employees who submitted bugs. But you can imagine like Windows has like many, many users, and the actual number of users who have an interest in bug reports is much higher. So the methodology that we used was like what I call a sandwich. So we essentially had some qualitative survey in the beginning, then we did some quantitative data analysis in the middle, and we followed up with another survey. And the main question that we asked in the initial survey was like, in your experience, how do each of a set of factors affect the chances of whether a bug will get successfully resolved as fixed? And we sent this to about 1,800 Microsoft, like Windows developers, and out of them, like 20% responded. And what we did next is essentially we looked at all bug reports that were in the Windows Vista database. So unfortunately, I can't tell you how many, but it was quite a bit. And we looked at certain factors like how does reputation of a bug reporter impact the chances of a bug getting fixed? What about the interest in a bug report, the number of reassignments, and the distance? And yeah, so let me show you some results. So the first thing which we looked at was at reputation. And this was partly motivated by one of the quotes that we got back from the initial survey. And the quote is, "A big influence on bug fixes is the reputation of a person opening the bug. If the submitter has a high history of submitting high-quality bugs, the new bugs from that person get better attention." Okay? So if you have a history of submitting high-quality bugs, that's good for your bug report. So that's essentially what we used to quantify the reputation. So essentially, for each bug report, we looked at the person who submitted the bug report. We checked how many bugs did the person open in the past, okay? And we checked how many of these bugs were actually fixed. And what we more or less did is we computed the percentage of fixed bugs. So you can see here there's like a +1. So it's not exactly the percentage. So the +1 was there for two reasons. Like first, it avoids division by 0. So that's the obvious reason. But the more more subtle reason is essentially it also introduces some weighting. Because if you think of a person who has submitted one bug report, which was fixed, what the person ends up is with 1/2, so with 0.5. Compared to a person with 100 bug reports, of which all 100 were fixed, you have 100/101, so it's a much higher value. And so what we essentially found is, so that's the result. I'm not showing the result yet, but essentially On the x-axis, you can see the reputation of a person who opened the bug. And on the y-axis, you see the likelihood that the bug was fixed. So unfortunately, I cannot show you the y-axis for the labels, but I'm sure you can figure it out. And essentially what we found is essentially that there was almost like a perfect correlation between the reputation of a bug opener and the chances that bugs get fixed, because what you can see here is like if you have a very low reputation, you have also a very low likelihood of your bug reports getting fixed, compared to when you have a very high reputation, it's very likely that your bug gets fixed. There were a few exceptions. Like for example, if you submit your first bug report, then your likelihood of a bug getting fixed would be here. So another thing which we looked at was at reassignments, and like actually quite a few people in research think like that reassignments are bad, and that they actually decrease the chances of bugs getting fixed. And we even had like a question in our survey to the Microsoft developers, and they thought the same. So we asked like, how does the bug report activity affect the chances of being successfully fixed? No reassignment, developers thought it increases the chances. If you have many reassignment, it decreases the chances. So what we found was actually not exactly this. It was slightly different. So we found that the lowest likelihood for bugs getting fixed is actually when you have no reassignments. Okay? For a few reassignments, it increases the likelihood of bugs getting fixed, and then it starts decreasing again. And so there was actually two reasons why this is the case. Like one is essentially that bug report reassignments are essentially part of a process. Like at Microsoft, when you have a bug report, usually someone fixes it, then it gets tested, and then it might go back to the developer for additional work. But essentially, usually multiple people are involved for a successful bug fix. And another thing is, like that's what we have a quote here, is that often bugs are submitted to different components. Like for example here, many times are exposed in the user interface, but are not caused by the team writing the UI code. These bugs can pass down several layers of components before landing on a lower level component owner. So in each of these levels corresponds to one reassignment. In the survey, we also asked about like other factors which influence the chances of bugs getting fixed. And like one which was pointed out was the quality of a bug report. So if you have a good quality bug report, higher chance of getting fixed. Poor quality, lower chance of getting fixed. Another one was the customer and business impact. So if there's a very high cost of not fixing the bug, then it's more likely to be fixed. Also, how senior or how high up the bug opener is. Like think of having a vice president who submits a bug report compared to an intern who submits a bug report. So that has some influence. And also for interpersonal skills. Remember I told you it's like a highly social process, bug fixing. Essentially what sometimes needs to happen is that people need to argue for a bug report. So they need to convince the person who's in charge of fixing the bug why this bug should be fixed. And essentially what came out of this research was we came up with a set of recommendations for how to improve the bug triaging process. Like one was essentially there needs to be some training for employees to write high quality bug reports. And not only needs to be for some training, you also need to have some incentive. So incentive, like what some projects in open source did is like they had like some special prize for the best bug report. And yeah. Also you need to increase the awareness of developers, because often like while we showed that reassignments are not necessarily bad, there's still quite a large number of reassignments that happen for no good reason. Because sometimes I just don't know who should fix the bug, so I just assign the bug report to Chris, and Chris then just says, hey, it's not my bug, assigns it back to me. Also, communication and trust, so that's related, like that's also a very important thing to improve. And also, it should be very objective in which bugs get higher priority than others. I briefly want to do a shout out to a related study. We also looked at what makes a good bug report, and there's a journal paper if you're interested in this one. So now, briefly want to talk about data-driven software engineering. So this is to connect to Wolfram Schulte's keynote this morning. And there are essentially many different questions that you look at in the empirical software engineering group. So here are just a few of them. So there are actually more. And essentially what we use to answer these questions is a combination of mining software repositories. So I'm not sure, like, if you haven't heard of mining software repositories, essentially what this is you take like existing repositories, like the version control system, the bug database, and you apply some sort of data mining technique to get some insight out of the repositories. And also, like another area where we use many techniques from is empirical software engineering. And if you think about this, like the way I usually explain it is like mining software repositories is focused a lot more on on doing things automatically, while empirical software engineering is really focused on getting insights, like getting very deep insight. And I think it will be important to essentially combine these two areas and move on to software development analytics. And so that's a slide from Wolfram's keynote. So essentially, the definition of analytics is quite interesting because it's very open. Like if you look at this one here, it says use of analysis, data, and systematic reasoning to make decisions. Okay? So if you look at it, like it's, so analysis can be anything, right? You can do some data mining, you can use some statistical techniques, you can survey people, you can interview people. Same for data, you can use almost any data to make decisions, and you can use almost any reasoning technique. So pretty much almost everything can fall in this definition, but there is one key point in this definition, and that's to make decisions. So we do all this analysis to make decisions. And as Wolfram pointed out, like these areas are very successful in using data to make decisions, but in software engineering, I think we still need to catch up a bit. And so here's like one, what I think is quite some success story in analytics, which is essentially web analytics, and they call it Web Analytics 2.0. And if you think about how web analytics looked like 15 years ago, like when I started using the web, like what many people had was like these counters, like so many people went to my web page. So that's what more or less analytics at this time was. Like you had a web page, you had a counter, you maybe broke it down by web page, maybe by country, but all you got was like a report. But if you look at it now, there are actually very sophisticated tools which allow you to interactively drill down into the data, slice it and dice it in very different ways. And it's not just this, what changed web analytics. They also realized that it's not just measurement, right? I don't know, like if you browse the web, what sometimes happens is that you get like an invitation to participate in a survey. So essentially, that's also what they realize is that they need more qualitative data. So they need to get feedback from customers how they use the web pages to build better web pages. And again, I think that's something which is missing in lots of decision making right now. So coming back to software development analytics, so there are two observations. I think it's two observations. Essentially, like the first one is that stakeholders have very different needs. Like many people in research think like from the researcher perspective, developer perspective, but really there are many other people, like you have testers, you have development leads, you have test leads, and you have managers who all want to get out something out of data, but they all ask very different questions. And most researchers are just focused on developers. Or some people are just focused on testing, but not many people think about all of them. And also, like essentially what this hints at is that you need different tools for different stakeholders. But I think we need to go one step further, is actually we need to have different tools for the same kind of stakeholder. And this goes back to the measurement and qualitative insights thing. Like essentially, if you just look at measurement, there's only so much you can find out. Like for example, you can find out that some metric has changed yesterday dramatically, but you don't really know why has it changed. And so you also, like you always have like two kinds of questions. Like first, what has happened and why has happened? And so essentially, a single tool won't be enough. So in short, I think like what the direction is, like we need to make the data that we collect right now more actionable and also more accessible. And there are 6 different directions where I think we can go. Like first, it's essentially about the data collection. Like lots of research is very data focused, especially in mining software repositories. We take a few repositories, we come up with a great research question, we come up with a great tool, and we hope that someone is starting using it. But really, the way that it should be the other way around. We start with the people. We want to find out what they need, and then we think about what data do we need to collect. So that's one direction for data collection. And the other one is essentially the integration of different data sources. Because right now we have like bug databases, we have version archives, we have communication, we have all kinds of documents, and they're not very tightly integrated. Another direction is essentially data quality, and that's where Chris did some very great research. If you think about it, you want to make a decision, and you want to base the decision on data. And if you do so, then the quality of the data should be really good, because if the quality is bad, you might end up doing the wrong decision, just because the data was wrong. So having said this, it doesn't mean that you need to have 100% correct data. For example, if you don't use certain data to make decisions, then the quality of this data doesn't really matter that much. Another direction is privacy, because data can be used to make many decisions, and many decisions also involve like people, like at workplaces. And so I think it's about time to start thinking about privacy. The fourth one is essentially about understanding the user needs. So this picture here shows essentially the organizational structure of a company. So I think most, like in research, we are really, really good on this level. Like we know a lot about developers, what their needs are, like what tools they need. I would argue that we don't know too much about managers, okay? And especially we don't know a lot about the communication that takes place between the different levels. And that's where typically data is used to make decisions. Like a manager uses some data to communicate a decision that he has made, either to his managers or to his reports. The fifth direction is essentially the user experience. Like you can have a great result or a great finding, but as long as you can present it to a user in an intuitive way, they probably won't act on the finding. So it's really about like thinking about how can we surface information, what's the best way to visualize insights. And the sixth direction is essentially, I think, for education, because like there's a huge interest in society right now to to become more data-driven. And I think it's also important for us to teach engineers like how to look at data, how to analyze data, how to understand research results. And that concludes the talk. If you're interested in our work, go to our webpage, Bing for it, Empirical Software Engineering at Microsoft. And thank you very much. Yeah.
Did you evaluate bug prediction?
Hmm?
Did you evaluate your bug prediction?
The bug, you mean?
So you had a bug prediction model, right?
Yeah. So
were there any evaluation results that you did?
well, we looked at, you mean like which bugs should be fixed or not? So we did an evaluation, but the thing is, so it turned out to be fairly okay. I think it was like 70% precision, 70% recall. But there was quite some pushback on using such models. And essentially, like first, like every bug is kind of unique, right? It's very hard. I don't think we should go for making decisions about which bugs should be fixed in an automatic fashion. So that's some of it that someone needs to look at. And that's also what most developers' opinion was.
So the moral of the story is that we should not look at bug prediction software.
I mean, like one of the reasons why we built this model was mostly to understand the interaction between the different factors. So you could use it for prediction, but it's not necessarily the best thing to do.
So you figured out the various features if someone wants to
Yeah.
develop a model.
Yeah, people could use it, but I think it's not a wise idea. Because essentially, like the 4 factors which contribute to whether a bug should be fixed, like first you want to look like what's the impact of a bug, how severe is the bug, how much would it cost to fix the bug, and I think how many users are affected. And that's something which is very hard to capture automatically. So that's why you can't automate this process. Yeah. Can you repeat? Yeah. Yeah, so there's some tools for duplicate detection. I don't have any studies at Microsoft, but there's quite a lot of research in open source. Yeah. Not in Microsoft. But there's some like, there's actually at FSE 2009, there was the debug advisor tool. So that's like one tool which people use for duplicate detection. Yeah.
So when you were talking about the effect on the likelihood of a bug being fixed at various features, you said, for example, that it affects the VP is more likely to get fixed than
Yep.
it only affects an intern at Microsoft. What if it only affects a mere customer? Because your entire talk about that seemed to be predicated on the understanding that it was Microsoft employees who submitted bugs. Is that because they act as an intermediary, or just because that's what you discussed?
So there are different databases where bugs are stored at Microsoft. So you have like the core bug database, which is used for development. Then you have the customer submitted bug database. And essentially, if a bug, like bugs from the customer database, then get propagated to the core bug database.
If it comes from a customer, this can't.
No. Like customer bugs are really important. So it's, yeah, they're probably more important than the VP. Because the VP should make his decisions based on what customers want. Yeah.
What would the main features identify for a bug? So for example, in my experience, I found that through the test case, bug is very, very likely to be fixed. But it's just like a high-level description, but it's much less likely. Do you have any data? For example, if you do the test case, is it always going to be fixed?
So I don't have any numbers on this. but like we made the same observation. Like if you have, the more information you provide, the more likely it is that your bug gets fixed. So I think we did some studies like before I joined Microsoft, I looked at bug triaging in open source, and where we found like if you have like stack traces or code examples, like your likelihood increases dramatically that a bug gets fixed. So there's one quote by Joel Spolsky, actually. Like he says, if you make like your UI for submitting bugs 10% easier to use, you get twice as many bug reports. So first, I would say yes, probably, but there's like a trade-off. Because if you make it easy for everyone to submit a bug report, then you might get way too many. So if you want to submit bug reports to Microsoft, go to connect.microsoft.com. Okay. Thank you.
Thank you very much. Well, Chris Bird here and Tom Zimmerman got ahead of me, and they used themselves. No, absolutely fine. But I can't possibly let that happen with our distinguished guest from Fraunhofer. And so I'm going to introduce you, Dieter. So this is Dieter Rombach, for those of you who don't know, and he has two positions. He is the, I've got to get this right, he has the chair of software engineering. It's a very nice chair to have. Kaiserslautern, and he's also the director of, the executive director of the Fraunhofer Institute of Experimental Software Engineering in Kaiserslautern. So Fraunhofer and Kaiserslautern TU. So what we've heard today from Microsoft is now being shown how it is done in Germany, and we look forward very much to your talk.
Okay.
Which actually happened because Dieter and I happened to be in Australia at the same time having a beer, and I said, well, Dieter, what about if you come to Paris? He said, oh, I love going to Paris. I said, well, will you give a talk? He said, sure. And here we are.
Thanks, Judith. First, it confirms again my statement that all my important collaborations started with a beer. Secondly, let me thank you, Judith, for the invitation, because I really enjoyed it. And I enjoyed it most of all because it's a very interesting extension of the communities I'm usually going to. It was interesting to find here lots of people I've seen for and met for 10, 20 years, but also people I've never met before. And that's a very nice extension, and so I've gotten feedback and information from different perspectives than I'm usually getting it, which is always helpful. So my talk is also on empirical studies or on empirical software engineering, and it's probably most closely connected to the data-driven software engineering. I have been involved in software development studies, software engineering studies of all kinds for many years. I worked for 10 years in the software engineering lab at NASA, which I always call the mother of all empirical labs. And I have continued doing this in Kaiserslautern for many years. But still, and I apologize for this because that might be due to my age or experience, I'm still a little bit frustrated about the overall impact of the studies we are doing. So we are doing nice studies, but overall, in terms of overall guidance for software development practice or also education, not that much improvement has been made. You know, I always envy my engineering colleagues because when they talk about physical laws and the students don't believe it, they go to the lab, then they believe it. Immediate feedback. When I talk about what I call software engineering laws, they go to the lab and do it differently. And you know what? The program might even work. So they don't believe really that well what I told them. And the reason is that our laws, and that's what I call cognitive laws, also I know I'm getting in trouble with the cognitive community with that for that, but I don't care anymore, is that they have a tremendous time lag. So it might work actually right now, and you made some valid points, but sometimes you better never touch the software again. Or if you have to change it a year down the road, then you find out that you actually violated some law or some rule or some guidance. but you didn't see this at the time when you were developing. So what I would like to do is actually to say, how can we take the next step and not only branch out into more studies, which is certainly necessary, and some of the things you highlighted, but also how can we create more quality kind of evidence out of these studies that eventually will be believed and will become the core of the science of software engineering, so that a developer, if you don't adhere to that, you are guilty of negligence. So if you're not following these guidelines, it's okay to take the responsibility, but then you take the responsibility. Today it's the other way around. I'm very often in front of courts when people are fighting. And typically, I mean, it's amazing how people from companies argue that there are no guidelines. We had to invent the wheel again. Yeah? So where does it come from? We have lots of these empirical results, but we have not thought about how much of this is only locally relevant, how much can we integrate, maybe it's valid for a domain, for a style of system, or maybe even, if you think as a scientist, for our entire discipline. Yeah, so we have lots of leaf level kinds of results, but we haven't aggregated them or made any effort to move towards that direction. Now, you will see, of course, that the problem is that in our field there is so many potential factors that you will never be able to cover everything. So I think we will never get to laws if the expectation is you have done enough experiments covering all possible kind of context situations. This is my ongoing fight with Dave Parnas, who keeps telling me you shouldn't do experimentation in software engineering because you will never do a good experiment. From a physical point of view, that's correct. We will never do an experiment where all the variables are covered enough. Yeah? So maybe on that side we are a little bit more on the social science side, that we have to decide based on our understanding what are the important impact factors, have to cover them, and then have to basically by community decision say, now that's enough evidence to say this should be a guideline or a rule for us to follow. Yeah? So it will never be the complete formal proof by means of experimentation. What's the expectation from some people from physics? So let me go into this and start with a small motivation, which is hopefully not too much recap, and then contrast a little bit, very briefly, traditional engineering, software engineering, and then I will talk a little bit about this distinction between observation, laws, and theories, where I see the trend may be going. And finally, I would like to excite you a little bit about a new activity we are trying to start, and maybe you might even be interested to join us. So motivation. Obviously, engineering requires, among other things, I'm not covering everything here, that we do understand and then we can predict. Otherwise, we will not be able to do data-driven software engineering. And if we know some of the constraints, that we can scale engineering based on regularities. Yeah? So we are very bad in scaling in the sense that's the result is what you described. That certain critical modules you better never touch again, because they were not designed for change. They were not designed for testing. They were just designed to provide a certain functionality. Maybe I should tell you why I'm maybe on a more strict side here. I'm coming actually from the embedded system world. And in embedded software systems, you have to provide quality of service guarantees. It's not valid enough to say we did our best or it was better. There is certain levels of quality you have to be able to guarantee. So if you want to do this, you have to have a process-product relationship, what engineers say. I have to use methods, tools, whatever, of which I know kind of what their impact is on what my quality goal is. Now you could argue, so stay with embedded systems. Now, unfortunately, today, we don't have that distinction anymore between embedded systems and information systems. We are this nice new label, cyber-physical systems. We are merging them more and more. Yeah? That means that's no longer something you can just do inside of embedded systems. It will become a challenge for all kinds of critical, social, whatever systems we are developing, as long as they are interrelated in some way with embedded systems. So traditional engineering disciplines do this based on physical laws. And as I said, I always envy them because the feedback is very quick. Software engineering partially uses empirical models. We have some of them we are using, mostly limited to very constrained domains. And the question is, that's the key question, could they eventually define the, I believe, cognitive laws in our field? So what we need to do is we need to expand empirical studies to all relevant process or product areas by means of replication. You mentioned some things that you would like to replicate this somewhere else. Why? Because then scientifically you have more evidence or better evidence. We might have to aggregate them to go from small processes to large processes. I remember at the time when I was at Maryland, we wanted to introduce together with IBM at the time, I'm sorry for that term here, in the context of a Microsoft building, but we wanted to introduce with Harlan Mills clean room development. And of course, you know you cannot do a real controlled or reasonably controlled study on such a huge process. So what was the approach? We thought, what are the critical new aspects, like using inspection for testing and so on? And so we did controlled experiments on the critical things, which we thought were the inhibitors for acceptance, and then aggregated the stuff and did only case studies on the entire process. I think that's one way of dealing with larger processes. You will never be able to run controlled experiments for huge development processes. Just the time lag and so on, the lack of control and so is impossible. Yeah? And we have to do this until they become qualitatively stable models. What I mean with qualitatively stable is we will never have life in physics that the use of a technique has exactly that as effect. There will always be variances because you're using it in different contexts. But I'm tempted to call it a law if the use of something always has a positive or always has a negative impact. Yeah? So for instance, in my environment, we did lots of studies on inspection techniques for requirements, and eventually a technique showed always positive impact. Sometimes it was only 10% reduction of rework, sometimes it was 50. It depended a little bit on the context of the company. But we didn't have, and other people replicated this, never a counter example. And so we were tempted to say, that's from our point of view a law that if you develop software in this domain, yeah, use inspections for requirements of that kind, you will have a positive impact on quality and rework reduction or cost. Yeah? Now, I'm not sure whether we can get much better, because there's always kinds of differences in different areas. But I think that's a much stronger statement than just listing 25 studies and saying, look, we have done this 25 times. It looks like a simple aggregation, but it says something so that every software developer who says, I want to achieve certain quality, or I want to reduce rework, has to be aware there is a technique that you should use to reduce this. If you don't use it, you take responsibility, and if it doesn't work, you should justify your decision, like other engineers do. It's reversing the responsibility. Not I, as a researcher or so, have to convince you that you should use this. No, it's our body of knowledge, and if that's your goal, you should use it, or you have a good reason for not doing it. Yeah, we know there is always situations where it's not justified, but then you take the responsibility. Yeah? That's what a body of knowledge means. Yeah? Also in building or in other engineering, people don't do always the same things. But they know if the risk is that, you should use certain techniques, otherwise you are in danger of getting into court if a building crumbles. So we need more than, of course, we need notations, languages, methods, and tools. As we discussed this morning, or after the meeting, we have heard so much about languages in the context of this meeting. How much knowledge do we have which languages, which type of languages are actually accepted and easily usable by normal developers of different kinds? Yeah? We make our assumptions. We, as the developers of languages, we like that and think it's good. Yeah? But how much knowledge do we really have to justify things like functional versus imperative or whatever it may be? Yeah? What is the normal developer, whether it's a sophisticated or less sophisticated, capable of using? Because if they don't want to use it, if we talked about user experience too, if they don't want to use it, if they can't use it, yeah, the result will be bad. Yeah? I always remembered how Dave Parnas told me how easy the 4-variable model is. And I said, sure, if you are part of the team. Yeah? I haven't seen that many organizations with 500, 5,000 developers to use it, because it's simply not trivial to use it. Yeah? We as scientists, researchers, very often think if we can use it effectively, it's ready for rollout. And there is a big step in between which empirical studies, I believe, can cover. But in the end, all notations, methods, and tools we are using in an organization, the critical ones at least, We should know under what circumstances what effects we do have. Now this I want to make very short. I mean, in physics, and this picture is not important, it's just giving a visual impression of regularity. We know that the physical laws guide them, and I told you before, that's the key for scaling engineering. Now, if you look at this, you get a visible recognition of there is something like divide and conquer. You could understand this entire thing by understanding modules and then composing them in some kind of predefined ways. And you could imagine if I need 4 more cores, how this could look like, if I need that. And this is true for all kinds of physical artifacts. Now, engineering practices, they have organized themselves in 3 layers, also in research, also in universities, everywhere. You have always some underlying mathematics. You have the scientific area, in this case, saying it's physics. And then you have the application of these laws in engineering practices. I actually believe one of the problems we do have is we don't know what is science and what's engineering in our field. We mix this very much, and you have computer science departments which are completely on the scientific side, and you have computer science departments which are completely on the engineering side. So, software engineering. Do you get a physical impression that the divide and conquer is used here? This is, by the way, a real system. About 10 million lines of code. For Microsoft, that might not be extremely high, but for us, this is a reasonably big system. And we very often do reverse engineering. We have tools for that to show the structure and visibly convince people why they might have a problem maintaining that system. This was a system, which I will not mention the name of, which every new release, the system went down for 1 week. And they couldn't tolerate this. And so eventually we tried to convince them that this was not an isolated problem, this was a general problem. In addition, we found out that the system had 4,000 violations of the actual architecture. This is the actual architecture and the specified architecture. So if you came as a new guy on board to maintain the system, and you looked at the documented architecture, you better throw it away. It might mislead you more than help. So it's a big problem how we deal with the concepts of design for testability, design for modifiability is not established in our field. And this is what I said before. The guys go out of my class, some of them at least, go into the lab, hack something, violating all the things we talked about, and it works at some point in time. But it's only a question of time until you should never touch this again. And by the way, I do not believe that considering this does increase cost, on the contrary. I have always experienced in my entire professional life, if you do the right thing, it costs less. Unless you do over-engineering. I'm not talking about over-engineering. I'm just doing the project you want to do the right way. And so empirical studies to some extent also help. Visualization is an important part of measurement, because very often the data itself is not self-explanatory. You may use some kind of visual metaphor or so to convey that to people in a better way. And this helps actually to get some of this across. Now, how are we organized? Now, that's from my point of view how we should be organized. We also need some kind of, mathematics is slightly different, large amount of discrete mathematics, but not only. This, from my point of view, computer science is whatever the foundations are, the science, we are not clear on that, and the application of this in building large artifacts. Ignore the other one. One important reason I believe in that structure is when we develop systems or are involved, it's very hard to speak to engineering people if you don't have kind of a similar view of your area. It's hardware, software, and either we are talking about science or we talk about engineering. This kind of structure is much more helpful for this. Today, in most departments, this is in the same department. And it depends a little bit on the history. Some were created out of mathematics, some more from electrical engineering, Nachrichtentechnik in German, and they have different perspectives on things. Now, what's the role of empirical studies here? Does it belong here or here? It depends. I mean, even in my very basic work, we do, in that case, mostly controlled experiments to have a first understanding of what we are doing has certain benefits. But on the other hand, engineering should never be done without learning something. So we are proclaiming that every project should be viewed as a case study to piggyback on it. Some things I want to learn, otherwise it's a waste from that point of view. Modeling, because empirical studies is one thing, but what are the models you are creating? Relevant for a domain or relevant for the community at large? Again, you have the same thing. I mean, here in computer science, we do modeling. We are trying to understand, for instance, in your case, or in the case of testing, you have different techniques you are developing. How well are they working? So, by means of controlled experiments. But if you want to do this for organizations, for instance, the body of knowledge for Microsoft, or for Siemens, whatever, or even larger, then this is something that will take place based on lessons from engineering. So empirical studies and modeling is part of the science aspect of our field as well as the engineering. Now, this here I only put up to say no excuses accepted that we can do this. I mean, we have 25 years of history that we can do experiments, purely. Experiments I'm now using for control as well as case studies, that we can do that. The hindrance is typically not the technology, the methods we do use, but it is, I would say, the understanding that something like this is needed. Especially in companies I have a lot to do with where engineers are running a company, where you would expect that they are very close to something like this, but they don't understand this kind of experimentation and support it very well. By the way, these are just our methods we are using for setting up measurement programs. So a lot what you said about stakeholders, privacy, that's exactly why we developed this, because we said it's not enough to say what do you measure. You have to have that context. Or how do you piggyback a case study on a real project, this QIP, or how to organize and package this. So we have tools in place, and I'm not saying these are the only ones. I'm saying there are tools. Yeah? If you're using something similar, that's fine. To run studies and build models. So how do they look like? I mean, I apologize, I do this in a nutshell. What I'm saying is for prediction models, and think, for instance, of the COCOMO model, predicting effort based on size. You are typically trying to predict something related to quality, productivity, or time. In this case, it was cost, and the model was a model of the life cycle of the entire development process. Yeah? So you have an effort model for that. And you want to predict it based on a model. This A2 would be, in terms of COCOMO, a system model to capture size, either lines of code or some kind of complexity. And you predict the impact of this on cost depending on some independent variables. I call this context. Yeah, so it's different whether you have experienced people, less experienced. It's different whether you are in a large system environment, small system environment. What all these impacting factors might be, and I put here hidden context, because one thing we have learned, if we have very valid models from one environment and another environment, and we really understand well the impact, if we try to merge them, suddenly things that were constant here and constant here become variable if you merge it, and you screw the entire result. So that's a very important aspect. We use qualitative analysis, of course, for this. You can't always do this quantitatively if we try to build larger models. Now, I don't explain all this, just a few things. The relationship is obviously not deterministic, because we are focusing on human-based kind of processes. Most of them are human-based. And the variance, which is here indicated plus minus 5 or 10%, depends on that you have a sufficient number of data points, that you have captured all the independent variables, and that the ones you are not capturing are reasonably stable. Yeah? Then you can get a reasonably stable prediction. For instance, we have for many companies in Germany done this for inspections, where plus minus 5% is not impossible. It's a few cycles of learning, and you have a very stable prediction model. Now, we use, as I said, qualitative analysis to find these hidden context vectors when we merge things, and obviously the variance can increase again if we do this. So if we have these hidden context variables, and so what do you do if you merge two things? We do the same thing we do for product lines. If we try to merge two and realize the span is too wide, then we do two product lines. The same here, if we merge it and the variance gets too high, we keep them as two separate models. Yeah? Then obviously the difference is too big to throw them under one umbrella. So, but here nothing new. That's the same thing we have done for years in architecture and product line engineering. So for what scope of projects or products do you have one reference architecture? And when is it more helpful or more efficient to have two reference architectures? Now, most of the empirical models of this kind, and this is a small, are of this form of partial functions. So for different kinds of context sets, you have different results. So for instance, the testing technique, and let's say you were interested in the percentage of defects you find 85% if you have a certain limited code complexity and the experience of people is high. And you might have different kinds of results if it's different. Now, this is, however, a very valid description for someone defining a project, because if you define a project, you have goals and constraints. The engineer asks, I want to achieve that goal, and I have the following constraints. Give me a process that works. So you would go in there, I have to build a project where based on my process model, I want to find 85%. I have experienced developers, and we have guidelines in place that the code complexity stays below a certain level. Then this technique gives me a certain result. Yeah? If not, I use something else. If I don't find something, I do hypothesis-based. Overall, you can imagine, if you think about these predictive models, you can have four kinds, where you relate product aspect to product aspects. Let's say something in the earlier phase to later phase. Product process, process, and process product. This is really the one that is most closely related to these process-product relationships every engineer talks about. So for instance, the test model here is one of that kind. Now, what exists today? I think most people would say not enough. What do I mean by observations, laws, and theories, to put this into context? Observations are, I have done one study, and I have no idea whether I will repeat the trend, nor the quantitative result if I do it one more time. At least I don't know. Yeah, that's what I call observation. One single point. I call it a law. If I have a representative set of studies, and what's representative? I mean, community people who understand that domain have to decide. Did I cover all critical aspects or not? That's what I said before. My controversy with Dave Parnas, we will not be able to cover everything. Yeah? And I'm reasonably certain that I have qualitative stability. So what I said before, it will always be better or always be worse. Not quantitatively. If you want to have quantitative stability, you really need to have a theory, which means you understand all impacting factors. That's really a long way to go. Yeah? We don't have that many theories except for very, very, very constrained areas. My goal is to move during my lifetime, and so this has to happen pretty quickly. I'm already one of the older guys here. At least have a set of what are the 20 laws, like, for instance, what Barry Boehm always said, that if you find defects early, they are cheap. So if you have this problem, use a certain inspection technique. It will always buy you quality and reduced effort. How many of these can we find that we can say they should be on a short list of every developer? And either you satisfy them, or you better have a good reason why not to do it. So what exists are today mostly observations. We have some laws, but we need more of the latter one. So the existing body of knowledge, there is a lot. We have developed experience bases for ourselves, for our technologies we are selling, but also together with companies, for instance with Bosch together, there is an empirical lab where they try to develop these models for all their, what they call best practices. It's amazing, they call them best practices before they knew well they're best. But they are already best practices, and now we are trying to substantiate this or qualify this. There's also a large body. I once did an effort with a colleague of mine to write together things, and it's amazing how many facts exist. but still we need to do more, and we have to make sure that we don't have these little areas. There is a little bit of Microsoft experience, there's a little bit of Siemens experience, and so on. This helps companies, but it does not add to the body of knowledge for us as a community, which I would like to see reflected in teaching, as well as in general practices. So eventually in front of a court, I would like to be able to apply these criteria if someone says, I have done a good job. Because if you haven't applied them, you haven't done a good job. Like, if you an example, VW had a problem that a child got killed because on the front seat, the baby seat, the airbag was sharp, and so the child died. Now the excuse was the guy brought the car to a shop, the battery was taken off, they was tapped back on, and it went into default mode, which was on. Yeah, so the child. Now I would say if you build software for such safety critical systems, you should know about reachability analysis, define critical states, and guarantee that they can't be reached. Now these people didn't even know about these techniques. Yeah, so I'm just saying from a professional point of view, they should not be involved in this kind of software. And it's amazing that with all their lawyers, they can get around this in front of a court. Yeah. So I skip this. Just to have a view, you can actually, through our internet site, for all the techniques, this is, for instance, how we apply this SAFE. This is the tool that reverse engineers the architecture, which you now can apply live. So anytime you make a programming decision, the system tells you whether you violate the specified architecture. Yeah? And so we have made evaluations. All these are evaluations with industry customers. And there is a whole list of this. So everything we are offering, at least we are trying to do the job. Experimental software engineering means not experimentally building software. It means we bring things to the lab to experiment with them. So we can go to customers and have a certain sense what they're good for and bad. And my experience is we are reducing the gap for introducing new things by that to a point where a company thinks it's manageable. They don't feel like they're guinea pigs anymore. They have some evidence. I mean, we can provide 100% evidence because then we would have to do the studies in their context. So I'm not going through this. There is a large number of things I could talk about, but this is something you can also see in the internet. Maybe this as a reference. I'm using this V model for experimentation for all my PhD students, not only. Yeah? So they follow this model. They have to, based on state of the practice analysis, define a problem, a hypothesis. Then they have to think about one solution approach. So think about the problem is companies have too much rework. Then you say one way of addressing this is defining a new inspection technique that finds more defects. Then you do your research, develop this, and then you experiment. The first is a technology-focused experiment where you compare this to others in a controlled way where you find more defects. But then you integrate it into the development process of this domain and see whether, because there's lots of things that can have a benefit in isolation. They will not have a benefit when you integrate them. So this is the controlled experiment, mostly controlled experiment, not exclusively, and this is then more case studies we do in conjunction with our industry partners. Now this is the book I wrote many years ago, and there are things described which we call laws or whatever term you want to use. And some of them look very obvious, but the point was it's not being followed up on them. Yeah? So if you say requirements deficiencies are the prime source of project failures, there is a certain domain behind this. I have here only listed the references. Then there is possible solutions. Now, it would be nice if I would, of course, have models that say, do I have inspections or do I have different inspections and know which one is better? Then we are really in engineering. We make choices about process based on facts. Now, also inspections, we have laws. But what I would like to close with, to not run out of time too much, is we are currently really trying to put together an effort to take a first step into aggregation. And we are trying to find several companies, probably within a domain. We have very large projects in Germany where we have aerospace, automotive, and so on. Several companies that are guinea pigs, so to speak, where we do experiments for instance, model-driven development. And the idea is you can do this at different levels. You can do this for research organizations, like we did it for our competencies. You could do it for Microsoft Research, what you do. You could do it for development organization, which is already more complex. Yeah? But the focus here would be for key processes they use in their development, or maybe new ones they want to introduce. And really what I try to pitch here is we want to go beyond one company. We want to work towards community at large laws. And so we have already convinced Springer, who wanted to have a second edition of our book. And I said, you know, the purpose of the book was to just show there is enough already. It's not the right media to maintain the body of knowledge. So now what we are doing is actually not writing a book, but they will maintain a version where companies can buy not the entire book, but something related to a technology, to a domain. And in the background, they will actually host a database to continue evolving this. So we would probably be responsible for content management. And when do you call something a law? As I said before, there has to be some accepted peers from, let's say, the design, inspection, testing community who say, to make it a law for this domain, or in general, we have covered all bases enough to make that judgment call. I mean, this is, by the way, very often done in medicine and other social sciences, where you could never come to a conclusion if you would wait for complete coverage. Yeah? So you have to have experts who say, if you have covered that, that is grounds for saying, we think in general this applies. They might be wrong once in a while, otherwise nobody would die of medication, but in most of the cases they might be right. And I see this as the only way, if we want to go from the huge set of little plans of empirical evidence to something that will shape our discipline in more general terms. And we'll not do this in one step. So when I say here community at large, of course, that's too much. We want to capture, let's say, with 5 or 10 companies in one domain. That's the idea. And so there's lots of questions here, of course. I believe the time is right to shift to the next gear. We need to do more studies, but I think we also need to elevate this. Who wants to participate? Actively, I mean. And the most important thing is, because I have been involved in several smaller experiments like this or activities like this, how do you provide the incentive for others to participate, to contribute? Reflections, new insights, whatsoever. Because here we have to have quality of use. Yeah? We have to user experience. We have to make it nice. And this might be something actually, besides the empirical stuff, where Microsoft could contribute something. So we can't have a standalone tool where we say, input your experiences. Yeah? That's not going to work. It has to be part of something else. That is a side effect, and there is fun, there might be a reward, there might be something that makes it exciting for people to contribute. Also what they get back in terms of accumulated experiences. So this is my plan for the next 5 years. I'm not sure whether it will succeed, but I'm certainly willing to take an effort to bring this to the next level. Thanks a lot.
Thank you very much, Peter. Okay, got some questions on that? So I have a question.
I'm tired.
What do you think would be the single driver that would assist your plan? The thing that you could do that would...
I mean, first of all, probably pick a large representative domain within Microsoft and do it. Mm-hmm. But that would be more for Microsoft. I mean, you have lots of individual experiences lying around, so to speak. Yeah? But how many of these are really used by? What would it take for practitioners to pick this up? Yeah? So it's more in terms of we understand, but how do you make it proactively used? And the second thing is in terms of, I mean, Microsoft, after all, is the most widely distributed software on laptops and phones. So how can we, I mean, developers use this too. We talked about different paradigms of developers. How can we incentivize them to not only use this for development, but provide some, maybe controlled feedback so we can get experience? Yeah? Because you are doing the data mining, which is a very valuable thing. But it's very limited also, it's limited to certain questions. Yeah? Other questions you have to do partly accompanying projects. And that's the part where I say, how can we incentivize them to provide that feedback? I have a few ideas, but this is something we should talk about because it might also depend a lot on which community you are addressing. Yeah? But all the new things that have been developed about new models for development involving developers, yeah? I mean, it should be instrumented in a nice way to gain that kind of experience. And again, I mean, you said it, the data security issue and so on. Yeah?
Excellent. All right, well, we're going to carry on outside there so that people can go. And thank you very much.
You're welcome.